All right, well, 3 after, so we'll go ahead and get started. Like I said, I wouldn't be surprised if people roll in late because of the bad traffic. So how's everybody doing? Good? Good week? All right. So who remembers what we talked about last week? Units and conversions? Pretty simple, straightforward stuff, right? I don't think I was rocking anybody's world last week. Okay, maybe a bit for some of the people who haven't completed chemistry yet. I know there's a couple. But the moles and mass conversions are pretty straightforward, right? So do we have any questions before we move into tonight? Okay, great. So tonight we're going to talk about engineering mechanics. But first, I want to talk about 2 types of engineering that use engineering or utilize engineering mechanics more than probably any other. One of those is civil engineering. Does anybody here want to be a civil engineer? I don't have my list in front of me, but I know we had 1 or 2, but maybe not here. Okay, so does anybody know what a civil engineer does? What do they do, sir?
Yes, they're the guys that design and build the things for the community. Right.
Yeah, so civil engineers are basically the fundamental type of engineer. You have your hand up. What do you think they do? Architects? Okay, that's not entirely true, right? Architects are actually kind of the scientists to the structural engineering world, right? They like to design things. Architects want them to look pretty, right? And a lot of times architects have to work with structural engineers to make sure that the architect's design actually can stand up, right? So they go back and forth. I remember one time I actually did a job shadow for a civil engineer, and when I was on that job shadow, he took me into the building. He showed me they had this cross beam that was going diagonal across the building, and he said they had to put it on the inside because the architect wanted the outside of the building to look pretty, right? So the building needed that to stay functional from an earthquake standpoint, but we still want the buildings to look nice, right? We don't want everything to be ugly just because they're functional, right? So we definitely need architects to keep us in check because we sometimes just go for functional. But architects are definitely not engineers. Now they have a lot of that type of training, right? They have to make sure there's enough bathrooms for people. They have to make sure that stairs are at code, stuff like that, right? If there's a fire in the building, architects are the ones responsible for making sure people can get out. They have to consider all of that, so they are very, very technical, but they're not engineers. Yes?
So architects are more for pretty rather than actually...
Yeah, I mean, that's a very basic way of saying it, but that sounds somewhat insulting to architects, and that's not the case, because like I said, there's a lot of technical knowledge that goes into being an architect, right? Like I said, I mean, think about it. If you have a floor that's, I don't know, an acre wide, and it's 70 floors up, and you have to make sure that in the case of a fire and event that people have to be able to evacuate that building quickly, they have to make sure they hit codes, all that stuff. So they have a lot of work. They have their own stuff to deal with, and we make sure that their designs will be functional and affordable. Okay, so civil engineers are primarily concerned with the development and maintenance of public infrastructure and services with the goal of meeting human needs, right? So the very first engineer, we talked about this a couple weeks ago, the very first engineer was probably some guy standing knee deep in a field full of water trying to figure out how to get the water out of the field, right? If you've ever looked at a parking lot and wondered why parking lot's slightly slanted, or if you've ever, is anybody here a runner? No cross-country people? You're a bit of a runner? Track? Okay, well, so yeah, fair enough. So have you ever gone running on the road and you notice that when you're on the left side of the road, this leg always has to go farther because the road's slanted, right? Why is the road doing that?
It's raining.
Right, so it can drain water, right? That's a civil engineer's job. That's why it was flooding in Los Angeles? Yeah. So, but no, I mean, that's fundamentally what they do, right? So civil engineers, we call them civies, right? Civies design and supervise construction of roads, highways, buildings, everything from a basic infrastructure standpoint. Like I said, if you've ever wondered why a road slopes towards the edge, or why a stormwater drain is where it is, or why that stormwater drain's flooding when it shouldn't be, maybe somebody screwed up, right? But that's what a civil engineer does. So civil engineering, like I said, it was basically pretty much the fundamental, if you think back to Roman times, building aqueducts and just figuring out how to get buildings to stand up, right? You guys probably at this point in your education have done the whole Roman and Greek columns thing where you had to know the difference between the three, right? That's all engineering, whether it was called engineering back then or not, right? It's functional engineering, okay? So structural engineers The structural engineers, as we were just talking about, right? They actually focus on buildings, structures, makes sense, right? Then you have transportation engineers there are traffic engineers, right? Whenever you go around a traffic circle and you're like, why the heck is this traffic circle here? That would be a transportation engineer. A water resource engineer, what do you think that guy does? Deals with water? Yeah. So the water resource engineer, is not only going to figure out how to keep it clean, but how to get it places. And in our fluids section, which we'll talk about in a couple weeks, we're going to talk about the challenges actually involved in maintaining pressure, figuring out how often you need pump lift stations and stuff like that, right? Geotechnical engineers, they're the ones who study the ground, right? So Benjamin is a structural engineer. He's got this building that'll stand up and it'll be awesome. But if it can't stand on the sand, if he's going to build it on the beach, that's probably not going to last very long. So the geotechnical engineer will come in there. Yes, sir?
So they'd also be the ones to help in case of earthquakes or...
Certainly, yeah, absolutely, yeah. So yeah, they're going to make sure that the plot of land that you're building on can withstand so much pound per square inch, that it'll be stable. They're the ones who are going to look at the earthquakes, right? What's going to happen if something shifts, stuff like that. An urban planning engineer is also a type of civil engineer, sometimes also called a municipal engineer. And they're the ones who are essentially figuring out how many people can we have living in this area because of right, we still have to be able to get electricity to everybody, we have to be able to get water to everybody, everybody's got to be able to go to the bathroom and have it not run down the middle of the street, right? They're going to figure that stuff out, right? How many ditches do we need to dig? And then construction engineers serve as the bridge between the actual construction workers, the guys actually building stuff, and the rest of the engineering design. Because just because we have something, right, so you're a structural engineer, let's say, right, and you've taken the architect's design, you've made it stand up, but maybe you haven't properly thought about a more efficient way to build it, right? So the construction engineer can come back to the guys who are actually swinging the hammers, and they say, hey, look, this design isn't quite functional, or it's going to cost a lot of money to do this. So they'll serve as a bridge and say, hey, here's how we're going to actually functionally do this, right? So there's many different layers where civil engineering comes in. Okay? So this is my friend, Raisa Lee. She's a PE. Does anybody know what a PE means? It's actually a professional engineer. But yes, principal engineer is more of a title. Professional engineering is actually a certification that you get. So after you get your engineering degree, actually usually your senior year, a lot of times you'll take it. It's called the FE, it's called the Fundamental of Engineering exam. You'll sit down and it's a huge day-long exam. Usually the first 4 hours are in your field, like yours. So if I was a chemical engineer, I'd sit down for the FE and I would take a 4-hour exam on chemical engineering. And then the next 4 hours are on basically general engineering. They'll ask you kind of general engineering questions, circuits, stuff like that, right? Actually, I think I have that flip. I think the general's in the morning and the specifics in the afternoon. So after you get your FE, you get a passing score on your FE, you go and you have to work for a certain number of years, and you actually have to be under the guidance of a licensed professional engineer. And then after you satisfy all that criteria, you get enough experience under your belt, you can sit for the professional engineering exam. And once you get that, you actually are certified to sign off on things, right? So they would be, Benjamin, the PE, would be able to say, this bridge is going to stand up, I stamp it officially. Or Dustin, the PE, is going to say, this electrical system is not going to catch fire, and you'll certify it and stamp it, right? So in the time that you're working under that, you'll be doing the work for them, you'll come to the PE, bring them your design, and they'll say, this is good, and they'll stamp it to certify it, or they won't, they'll make you go back and work it. Yes? It absolutely holds you accountable. Yeah, that's why it's no joke to get that degree. It's very hard. And actually, the gentleman who we have coming in next Tuesday, Nick Besson, he's an electrical engineer with Eaton. He just got his PE, I think 2 years ago now. But it was a big deal and a huge accomplishment for him. Okay, so Raisa is also PE. She now has moved on from this company, but at the time we did this interview with her, she worked for NRG Renewables. She's a civil engineer, and what she was in charge of for this project was putting in at the time, the largest solar field in all of California. And it's kind of cool, you can actually see it. If you go on Google Maps, you can see this grid-looking thing. And that's what she put in. So what she fundamentally does is she leads the teams that does this. So she's not the one actually out installing it. She's the one figuring out how they're going to solve the problems that come up when they're installing it, right? So we talked about the construction engineer fundamentally figuring out, all right, this is the design, but it's not going to work. How can we get as close to the design as cheaply as possible in the time constraints? So she's out there actually handling stuff in the field. And so you can see she actually has her hard hat on. She's out in the field. She's doing real stuff. Very smart woman. And she got her BS at University of Wisconsin-Madison. All right, so civil engineers, in 2015, this was the last data I could find at the BLS, 2015 median pay was 82.2, which boils down to 39.53 per hour. Engineers are very rarely paid hourly, right? That's just what it boils to on a 40-hour week. Do keep in mind that, sorry, most engineers don't work 40-hour weeks. You're going to work more than that. So once you start increasing, what happens if I increase my denominator? makes it go down, right? So you don't ever want to do the math on how much you make per hour because sometimes you get sad, okay? But the job outlook for the next 10 years is 8%. Remember we had talked earlier in the year how roughly the job outlook for engineering is 10% or so. It's 8%, so a little less. And the top 5 schools for civil engineering, number 1 is UC Berkeley. Number 2 is Georgia Tech. Number 3 is UIUC, University of Illinois Urbana-Champaign. Number 4 is UTA, UT Austin. And number 5 is MIT. All right, so next, let's talk about mechanical engineering. Some you guys in here want to be mechanicals. Did I see you nod? No? No mechanicals? Nobody wants to own it? Kind of, maybe? All right, fair enough. All right, so I'll talk to Lynn here on this one, since she's the only one that cares, apparently. All right, so mechanical engineers design and manufacture all sorts of devices. Mechies, we call them, work on power generating devices. They work on generators, combustion engines. However, they can also work on power generating devices such as tools, industrial production equipment, robots, automobiles, or aircraft. So in short, mechanical engineers create and maintain the processes that drive technology and industry. Okay? I will say mechanical engineers kind of take a lot of ribbing for being like the fundamental engineers sometimes in school, but these guys can do a lot of pretty cool stuff. I went to school with one guy who now works at Nike. He was part of his master's project. He was working with foams, right, which they would want to put in their shoes, and he now, or at least at the time he worked for Nike. I haven't followed his career since, but. Okay, 2016 median pay, 84, so pretty much in line with civil engineering. Typical entry level is bachelor's degree, so you can very easily go in there with a bachelor's degree. Now that doesn't mean you're going to be making 84 with your bachelor's degree. What that means is the average person with a mechanical engineering degree who's in a mechanical engineering job earns 84. Okay, and that job outlook is 9%, so pretty much right in line with what we talked about. Okay, top schools for mechanical engineering. Number 1 is MIT. That probably doesn't surprise very many of you. Number 2 is Stanford. Number 3 is Georgia Tech. So of course you'll see a lot of these schools coming back. And number 4 is University of Michigan. And now Berkeley, UC Berkeley is at number 5. Okay, so plenty of West Coast schools if you want to stay on this side of the country and keep your parents happy. All right, so engineering mechanics, very fundamental to both of the disciplines we just talked about, which is why I picked those guys. So does anybody know what engineering mechanics, what is mechanics? Let's forget the engineering part just for a second. Does anybody know what mechanics is? What? How things move, okay. That's actually like the perfect answer, okay. That's what we're studying, is how things move, or more so actually what we're going to be caring about today is how things don't move. Now why would we care about things not moving?
Because we don't want buildings to move, bridges to move, etc.
Perfect, right? And actually we want them to move a little.
Yeah, like not like visible.
But from a mass standpoint, overall standpoint, you are exactly correct, right? We don't want our buildings to move, because what happens if our building moves? Falls down, right? We don't want our bridge to move because it falls down. All right, perfect answer. Nice job, you guys. All right, so a little silly review just before we do this. Who remembers SOHCAHTOA? Sine equals opposite over hypotenuse. Cosine equals adjacent over hypotenuse. And tangent equals opposite over adjacent, right? And that's if we're talking about this guy. What's this guy? Theta, right? Theta is the angle, okay? So if I'm taking the tangent, it's the green, which is the opposite, divided by the adjacent. You guys can figure it out, right? Everybody knows this? If anybody doesn't, raise your hand. It's not a big deal. Okay, we're all good? All right, because this is fundamental to what we're talking about today. It's one of those questions like, when am I ever going to have to know this? The question is right now, okay? All right, so mechanics is the study of a rigid body's motion when forces are applied. Dustin, what do I mean when I say a rigid body? A building? Okay. Does anybody know what a non-rigid body is? Like a fluid is exactly correct, right? So the idea of a rigid body, now I can use this. Now we all understand that if I press on this, it is going to actually give a little bit, right? But from a fundamental standpoint, if I press on this, it maintains its shape. Okay, so that's what we mean by a rigid body, is some body that maintains its shape when a force is applied. Obviously, we all know that if we push on water, it's going to change its shape, right? And that's what she was exactly correct. A non-rigid body would be like a fluid. Okay, so we use rigid bodies because we want to not worry about what happens to the molecules inside. From an engineering mechanics standpoint, we just look at the whole thing as one body, right? We understand that if we were to push Daphne, that maybe part of her would indent, or maybe she'd trip and fall and she would change form, right? But fundamentally, we were just looking at Daphne as a whole being, a whole body, okay? So, like I said, the body in question can either be moving and at rest. So here's your first physics throwback. Acceleration of 0 means what? Constant velocity, right? Does that constant velocity have to mean 0? No, it doesn't, right? So let's consider something in orbit. Is that moving at a constant velocity? No, that's actually a correct answer, right? It's not. And why is that? Correct, right? And we'll get there in a second with vectors, but you're exactly correct, right? So the idea is, let's say we have a plane flying, let's go away from the orbital mechanics part, right? But let's say we have a plane, and let's just assume the Earth is flat for a second. Just for a second. I know it's not. Just for a second, assume that the Earth is flat, right? That plane's flying at whatever elevation. It has a force acting on it in what direction? Downward. And where else? And whichever way it's going. And then there's a force pushing back, right? So if that plane is not falling down, it must be exerting a force in which other direction? The upward direction, right? Because they have to upset, right? So if we wanted to, actually let's change examples. Let's go with a hot air balloon that's floating perfectly in place, right? What are the net forces on that balloon? What's a net force? It's the total, right? So let's think about it. Our balloon is being pulled downwards, right? So in order for it not to move downwards, it has to be going up, right? All right. So body in question can either be moving or at rest. And we are going to care largely about stable, okay? And that doesn't necessarily mean not moving. We just care about stable, okay? So engineering mechanics, what engineering mechanics is the application of what we just talked about to real world problems, like making a bridge not fall down, okay? Engineering mechanics is the application of physics to real world problems, okay? So statics is the study of bodies in equilibrium. And what do I mean by equilibrium? You guys just answered it. Net force equals what? 0. Because what's my equation for force? F equals ma. What's F is force. What's m? And what's a? A, or acceleration, correct. Right, so in order for F to equal 0, things can't have no mass, at least in our real world, right? So what has to equal 0 by definition? Acceleration, right? So in statics, for something not to move, acceleration and net force have to equal 0. Simple enough, right? I know it sounds super simple, and I know you guys are all over it, but it's going to matter. Okay? Dynamics is the study of bodies which are not equilibrium, and thus there's acceleration, right? It has to work that way. Okay? If you put an acceleration on something, it has to move. If you apply a force to something and there's something not balanced, it will move. Okay? So we were picking on Daphne before, right? If I push on her, unless she pushes back with the same force, she's going to move in one direction. And if she pushes back on me with too much force, she's going to move the other direction. Okay? So now Daphne nailed this one really well. Okay? So vectors. You guys have all done vector work at this point in your math career, right? Whether it be, looking at which direction a plane's going to go when the wind goes on it. That's a very common one, right? Planes moving in this direction with so much wind, where does it end up? Very common one. Okay? So what is a scalar? Just magnitude, no direction. Right? Very good. So scalar can be fully described with a single number. Examples of scalars are energy, mass, speed. Right? Speed and velocity are two different things. Right? I see a bunch of nods. That's good. Okay? Temperature and time. A vector quantity, as you guys are all nodding and you know, right? A vector quantity has both a magnitude and a direction. Okay? Examples are acceleration, displacement, force, and velocity. right, so vector diagrams, right? If this red line here is a vector, vector quantities are visually expressed by a vector diagram as below. So vector V, see I've got that little arrow over it. That's what we're going to use in this course to denote a vector. It's probably consistent with what you guys have seen already, I would assume. It becomes hard in the computer. I learned to do it with just like one arrow on it, right? But again, if it has the arrow on it, it's okay. Direction of vectors measured by an angle 0 from some known reference. Typically we use what? What do we typically use as 0? The ground, right? Because we're all standing on the ground, so if I want to go that direction, I'll use that, right? Okay. The length of this line segment indicates to some scale the magnitude of the vector. Now that becomes very tricky in practice, right? I think maybe when you guys started learning vectors, they had to use a ruler and you draw it with some scale to how it was supposed to be. And to be frank with you, that kind of becomes a waste of time, right? We can all just write a number above it. Now, obviously, if we've got a 1 and a 5, maybe it's going to look something like that, right? But I don't want you guys wasting a lot of time measuring out tick marks when we can all fundamentally look at it and understand, right? Diagrams are for us to understand, not for us to get exactly correct, and that's perfectly fine. All right, so component vectors. In a 2D system, and that's all we're going to be working with today, right? I know you guys can do 3D systems, but we can learn everything we need to know from a fundamental standpoint in 2D, so we don't really need to go into 3D, okay? So we're not going to get super complicated there. It's the same concept, it just makes the math harder, so there's no reason to go there, okay? So in a 2D system, any vector can be thought of as having an impact in 2 directions. In this case, right, our red vector that we had last time, it has an x component, which is the blue line, and it has a y component, which is the green line, right? How would I thus express that red vector in terms of the red or the blue line and the green line? Does anybody know how we do that? What's that? Pythagorean theorem. Okay. So, well, we're going to go use our trig, right? So in this case, if we let the angle between the vector and the x component equal theta, or it can be 1 minus theta and go the other way, right? Whichever way, as long as you guys know what you're using as your frame of reference. V, which is the absolute value of the vector, equals Vx squared plus Vy squared root. Vx equals absolute value cos theta, and Vy equals absolute value sine theta. And then you can find the angle by taking the tangent. Right? So was it Pythagorean theorem? Basically, right? It's just trig. Okay? So let's just be very clear on this, right? So if I want to find this, I've got a triangle here, right? Because this triangle translates, right? So this is, we're forming a square. And then that red line forms a triangle. So I can just use trig, right? Theta here. What's this equal to? Vy, right? So Vx, the x component, the y component. So if I want to find this, what would I take? Correct. And if I want to find this angle, what would it be? So Katoa, which one is it? So it's opposite over adjacent equals tangent, right? So you guys are just using your triangles, right? You guys are all over this. You guys did this. When did you guys do trig? Probably like middle school, maybe? Freshman year, maybe? Because you guys don't do geometry freshman year anymore, right? Yeah. I think, yeah, anyway, but everybody's seen this, right? All right, so here's our sample problem. Let's just make sure we've all got this down, okay? So, vector components. Oh, and I don't have the page on here, but we can figure it out real quick. You just turn to it, perfect. So this one is on page 9 in your book. The magnitude of vector A is 100 units, and the direction of the vector is 30 degrees with the horizontal. Find the components of the vector. And you're probably going to need a calculator for this one, or your phone, whatever. Okay, are we all ready? Ready enough? Good enough? All right, Daphne, you want to do this one for us? All right, so what did you get for the x component?
Around 86.
Okay, so how did you do it? Okay, 100 cosine of 30, so 100 times root 3 over 2 equals 50 root 3, which which equals, oh, I just did it that way, 50 root 3, but yeah, you're right. And then what did you get for AY? Y component, you got 50, perfect. All right, so for the Y component, right, so she did it perfectly, right? So all we're doing is we're taking the vector itself times cosine of 30, and that gives us the X component. The vector itself times the sine of 30 gives us the Y component, which is 50. Okay? All right, now vector addition, you guys have all done this. So in mechanics, we commonly encounter situations where an object is being acted upon by several forces, right? We already talked about that with the plane, where it was being acted on by 4 different forces. Okay? We determine the way these individual vectors combine through vector addition. Vector addition is the operation of adding 2 or more vectors together in a sum. The resultant, which is fundamentally what we care about, that's why it's red there, is the vector sum of 2 or more vectors. It is the result, so we call it the resultant, of adding those vectors together. So in this case, if I added A and B together, we would get R. Now it seems very fundamentally simple, right? You just put the 2 end to end and see where they end up by drawing a line. Okay? But that's very simple from a pictorial point of view, but it's not necessarily as simple from a math point of view until we think about it this way. Right? So what we see here is if we break these individual components down into, we break the individual vectors and down into their individual components, the one will have an X component, the other will have some amount of X component, the other will have some amount of Y component, the other will have some amount of Y component, and then all we have to do is add the X components together, add the Y components together, and then you just back solve using your equations to find the resultant R. Okay? Does that make sense? So in the case before, we had what we just did in our last example is we took a vector and we found the X and Y components. Right? Pretty simple to do. So now we would just do that for each vector that we have, add them up, and then what would we do to find R? Which equation would we use? Trigonometry. Perfect. Right? All right. Is there any questions on that? Simple enough? Okay. All right. The next thing, before we get into it, is a free body diagram. Does anybody here have any experience drawing free body diagrams? Yeah, see several hands. Good. Right. So, Benjamin, you said you've done this before, right? So, free body diagrams. What do I do when I'm drawing a free body diagram?
You draw all forces present on the object.
Do I care about the object itself? No. So all I'm doing in a free body diagram, he nailed it, you're correct. All we're doing in a free body diagram is we're drawing the forces acting on the object. So in this case, we have a ball that's sitting in a V, just like this, right? So we've got this thing here, it's sitting here like this, right? What are the forces acting on this balloon right now? Downward. What else? Upwards. Is it upwards? Yes. Lynn, you just did it. What did you do? So yeah, show me. Correct, right? So because the plates here are at an angle, right? They're pushing like this and pushing like this, right? If one was pushing more, what would happen to the balloon? It'd go this way, or it would go this way, right? So we have the downward force, then we have these two pushing it. Okay? And that's what we have there. We have force from board, and then the force from gravity itself. So what would I do here, Benjamin, for my free body diagram? It is essentially the free body diagram, except I might have them all just going to a point. But yes, free body diagram is essentially right here. Very good. All right, so this one should be page 10. All right, so what we're looking at here is a 20 Newton weight. So this is actually a real mechanics problem. This is something that you will actually take in an engineering mechanics. You will see this problem pop up in this type of problem, not this exact one. You see this type of problem is very common in an engineering mechanics course, right? So what do we essentially have here? Let's break this down together before we start getting into this. So this is page 11 in the books, correct? Okay, so page 11. So what do we actually have here? We have a 20 Newton weight suspended by 2 cables. So what I want you guys to do is draw the free body diagram for this weight, right? We don't have to solve anything yet, but what I care about is what's happening to this weight. So let's talk about this together, okay? So Chandler, what's one force acting on that 20 Newton weight? Gravity, perfect. So how are we going to draw that?
I would draw a line underneath the 20 Newton weight pointing down.
Okay, perfect. All right, Madison, what's another force I have acting on that weight? Okay, the string pulling it up this way, fair enough. And then the other string pulling it up the other way, right? So how are we going to draw that on the free body diagram? Going in each other direction. Now, what we want to make sure we do on the free body diagram is this. So here's how I drew it. So we have the 20 newtons going down, right? Because remember, 20 newtons is a force, not a weight, right? That's why I had 20 newtons. It makes it easier. So 20 newtons is going down, and then you have the one string pulling at 60 degrees from the norm, whatever. We'll just call it from the reference point, which makes sense to do it flat. Otherwise, because if we don't do it flat, what happens to our gravity? Then it's going at an angle, right? So put it at reference to the ground, okay? And then we have the other one going at 30 degrees. Now, how come my string is at 60 degrees from the roof and my other string is at 30 degrees from the roof, but yet the string is 60 degrees from the ground and 30 degrees from the ground? Why is that? Alternating angles. It's just geometry, right? So all this stuff that you had to learn in school all of a sudden starts coming together. Welcome to engineering. Okay? All right, so statics. Now we're back into it. Statics is what? Stuff that doesn't move. Bodies in equilibrium, stuff that doesn't move. Okay? So for a body to be in equilibrium, like we already talked about, the sum of forces has to be 0. And now, but we're not talking about just things in general. We're talking about things in how many dimensions? 2 dimensions is what we're going to focus on, but fundamentally, it has to be equivalent not only total force, but remember, forces are directional. So the forces in all directions have to be the same. Otherwise, what happens? It moves. It accelerates. Correct. It accelerates. Okay? Net force is always 0 on equilibrium. And this is the foundational concept of statics. And it says statistics there because I mistyped, but it's statics. Okay? All right. So this is what we already saw in that last one where we were doing the free body diagram. This is a very common statics problem. Okay? Common statics problem involves analysis of forces acting on a hanging object, maybe a sliding object, something like that. Okay? So in this case, we have our weight. This is very similar to the problem we just saw. The x component balance is simply cosine, because that's what's flat, minus or plus, depending on if you want to do subtracting a negative, right? We all get that. Now, why are they minus? Why is it cosine of A minus cosine of B? Why is that? Because they're in opposite directions, right? If they were pulling together, they would add. But because they're pushing against each other, they have to cancel. And why does it make sense that this has to cancel? Why do these two have to cancel? Why does that make sense? What's that? Because it's an equilibrium, right? If this one was pulling harder than this guy, what would happen? It'd move, and vice versa, right? And of course, they also have to have their components that equal what? The weight force down. Otherwise, what happens? The strings break, right? And your building falls down. Okay? So this is all very simple stuff. Fundamentally, I realize, but it's all very, and that's kind of the point, right? Isn't that what's great about this? It's all simple stuff that you guys already know how to do, and you guys can go be structural engineers now. No, I mean, seriously, you guys have it. Now you just need to go apply it to much larger, bigger problems, and you probably need Excel and computer programs to help you do it. But, right, so let's take a minute and talk about engineering structures. So an engineering structure is a system of interconnected bodies built to both support or transfer forces and easily withstand the loads supported to it. So let's pick on Lynn. What are you doing right now, Lynn? Sitting. Perfect. So your chair, that was the correct answer. Your chair is doing what? Okay. Is it moving? No, right? So your chair in of itself is an engineering structure, right? My camera over there is on a tripod. That tripod is an engineering structure, right? So we fundamentally a lot of times think of like a crane or a building or a bridge being an engineering structure, but your chair is an engineering structure, this table is an engineering structure, right? Okay, because they do exactly what they're supposed to do. They have a load that's being applied to it, which in this case is Lynn, It's fighting between Lynn and the floor, and it's holding its ground, and that's why she's able to sit here and not fall on her butt, all right? Okay. So, does anybody know what structural analysis is? And the answer is not simply the analysis of structures. That's not what I'm looking for, right? What is structural analysis?
Design again.
Say it again.
You analyze the forces on the design and basically see if it holds.
Perfect, right? And what do I mean by it holds? Doesn't break? What would the total forces on the structure have to be for it to hold and not break? And we're back home, right? You guys all know where I'm going with this, okay? So, structural analysis. Structural components are referred to as members or structural elements, okay? Because the structure as a whole is dependent on all of the smaller parts, right? Let's think about it again with the desk, Lynn's desk. What happens if I take one of the legs of your desk away? Is it going to stand up? Arguably, actually looking at your desk design, I could arguably take this one away and you could maybe balance yourself, right? But if I take that back one away, you're on your butt, or probably actually you're on your head, right? Okay? All parts of that desk have to work together to stand up. Okay? If one of them fails, the whole thing is going to fall apart, or potentially fall apart. Okay? So, because the structures depend on all the smaller parts, this is where structural analysis comes in. We have to actually look at the forces on each individual member. And we'll get into more on why the forces on each individual matter later on in the year when we get into materials engineering, looking at actually like the strength of what those different materials are made out of and how that matters. But fundamentally for now, what I want you guys to just think about is whether or not something can withstand the force and how much force is being applied to it. Okay? So, in order to start understanding, so what we have here, right, is this triangle. Very, very, very simple engineering diagram. And now if I do the force balance on it, I start looking at the forces this actually have. If I apply this load to the tip, what reaction forces occur? Coming up from the ground, right? The ground's pressing on it. So it's being what? It's being squished. What's the word for that? Compressed, correct. But these guys, if it was just this pencil, that I was pressing on, right? I'm pressing on both ends of this. Which direction are they going? Just simply up and down, right? There's nowhere else to go. But now, oh, that's not what there we go. All right, so now I have two pencils. If I press on the tip of these pencils, which way are they going to go? All right, so let's do it, right? They're going to go like that, right? And that's why we have this third member here at the bottom. What is this guy doing? What's that? He's holding them together, right? So you just nailed it. You said tension, okay? So we all agree that the structure as a whole is under compression, right? We all agree that we're being squished. So the structure as a whole is being squished, but is each member being squished? The answer is no, because of what you just said, sir. This one is under compression, it's being compressed. This one's under compression, it's being compressed. But the bar here that's holding them together, it's actually being pulled apart. And it has to be able to have a tensile force that can hold that structure together. Right? So that's what we're looking at. We're looking at here, a compressive force, and that's why the air is going towards each other. Compressive force here, and then this guy is being pulled apart. Okay, and that's what we're going to start doing when we go into structural analysis. Make sure I get Dr. Hampton's stuff for back in the right spot. All right, so we already talked about you guys just touched on some forces. So there are four, there's actually five, but there are four primary types of forces that are applied to objects, materials, whatever. The first is tension. Tension causes deformation which lengthens the object but narrows it, right? So like let's say I had a jar of silly putty or Play-Doh or something like that, right? If I were to take that clump of Play-Doh, the clump of Play-Doh still weighs the same amount, right? I still have the same volume of Play-Doh. And if I start pulling it apart, what has to happen to it? It stretches, but what does that mean by it stretching? It gets longer, but what happens in the center? It gets weaker, right? That's correct. But it starts getting thinner, right? And if I press on something, if I press on this guy, what's going to happen to him? gets fatter, right? So he gets shorter, but fatter, right? Kind of like me when I'm old, okay? The next type of force is shearing. So shearing is what would happen if I were to do something like this. I would move against each other. And what happens in this case is the top of something goes one direction, the bottom goes the other direction, and what ends up happening to the rest of the material? Yeah, it starts, what happens is that, I mean, again, I don't want to get too into it because we're going to talk about this in depth once we get towards the end of the semester. What happens is the molecules literally start rubbing against each other, right? So the entire thing is under strain. Think about it. One part wants to go this way, another part wants to go this way. You would not like it very much if I was moving your head in one direction and your feet in the other direction, right? It wouldn't end well, okay? And then the next is torsion, which is twisting. And this is actually fundamentally the same concept as shearing. It's actually doing the same thing, just in a twisting motion, right? So this would, what would be a good example of something under torsion? Wringing a towel. Yeah, the best example I can think of is a screw, right? Screwing something in, right? You're twisting it, you're causing, right? It's being pushed back as it's trying to go into the wood. It's under a type of shearing stress, okay? All right, and then next is one that you're going to see your structures under a lot, and this is bending. So bending itself is not a type of deformation. What happens in bending is, let's see if I can do something that not break it, right? In bending, very simpler, we're just going like this, right? My diagram up there, what happens is I'm actually pressing the top surface together, and I'm pulling the bottom surface apart. All right, so it's not that I'm bending this, it's that part of it is under tension and part of it is under compression, and the result is bending, because what happens? Something under tension gets longer, something under compression gets shorter, right? So the top's getting shorter, the bottom is getting longer. Okay? Does anybody know what usually breaks first? So if I were to keep, I'm not going to do it, but if I were to keep bending that until it broke, and we were to go in and look at it on a super slow motion camera, which side would it break from? Well, the middle is correct, but which would it break on, the stretching side or the compression side? Okay, you guys are all correct. Stretching side. Why would it break on the stretching side? Because of stretching. Fair. Yeah, so it generally, and again, this is more materials engineering, but as a general rule, most materials have a lower fracture point under tension than they do under compression, right? A great example of that, probably the easiest example of that, is concrete, right? Concrete can take a ton of pounding, right? We can jump up and down on concrete, no problem. But what happens to concrete during the summer when it gets hot and expands? It cracks, right? That's why sidewalks have built-in cracks every 3 or so feet, right, is to allow for expansion. Because if you just don't provide any spot for it, the concrete will expand and it'll crack. Or it'll contract too much in the winter and it'll crack. Okay? So, does that all make sense? We've all got that down? So bending is a combination of compression and what? Tension. Good. Okay, so strength of shapes. You may notice, looking around at various buildings and stuff, that a lot of buildings tend to be fundamentally the same. How many round buildings do we see? And by round, I don't mean like top-down shape, but like how many spherical buildings do we see? There's a couple of them out there in the world, and generally they're considered pieces of art, right? Because they're not actually that functional, right? So there's a lot of shapes that we use over and over and over again. All shapes, though, aren't created equal. Does anybody want to cheat ahead and tell me what the strongest shape is? Triangle. Everybody got it, right? Because you guys have all taken geometry, okay? So a rectangle, even a small load applied to a rectangle can cause it to deform. And what do I mean by that? I mean that it's actually changing shape. I don't mean that anything's breaking. And that's the important part here, right? So what happens is I apply a load to the side of this rectangle here. It's just going to bend over. Nothing has to break. Maybe some welds at the corners or whatever, depending on your structure, right? But if I had this all connected with just pin joints, flex joints, nothing has to change shape for it to deform. Does that make sense? Because I wouldn't have to pull on anything, I wouldn't have to compress anything, I wouldn't have to break any of the structures. All those structures are fine, Doesn't matter if that's the strongest material in the world. If it's built like that, it's still going to deform. It doesn't matter. Okay? But a triangle, like you guys correctly said, used correctly, the triangle is the strongest shape that can be built into a structure. So let me go back a slide. And again, I want to look at that. Why is a triangle the strongest shape? Why? All the sides are supporting each other, but all the sides there are connected. They're not? Why is that? There you go, right? Is that what you were going to say? Yeah. Yes. Yes. So you guys are exactly correct. Okay? So what happens in a triangle is triangle cannot be deformed without either breaking a joint or deforming one of the sides. Right? And by that I mean stretching, cracking, breaking, whatever. Okay? All other shapes out there, every single other shape can somehow be deformed because their angles are not fixed. Triangle is the only one that has to maintain a fixed angle, otherwise it breaks. Okay? And thus, the triangle is a fundamental component in geometric design of engineering structures. So what does that mean for us? Do we have buildings that are triangles out there? No. But we can do reinforcement in structural design. Very simple, we add a brace. What just happened, right? We just took a rectangle, we added a rectangular brace, and what just happened? Created two triangles, right? Mind-blowing, right? This is not high-level stuff, and that's what makes it awesome. So a brace that is under compression, and this is not a vocab test, right? I'm not going to hide the book. I'm just telling you this, right? But a brace that's under compression is called a strut, and a brace that is under tension is called a tie, right? So bridges will have both struts and ties, but fundamentally they're just all braces, okay? All right, so now if you could go to, yep, Lynn's already ahead of me, right? So now if you could go to, I believe it's page 13. Okay, so what we have here are we have several shapes, and what I'd like you to do is draw in struts and or ties. Again, I don't really care about the vocabulary. Maybe your engineering professor will later. But I'd like you to draw in struts and or ties, which means what? Straight lines, right? A single supporting member in each of these shapes below, in a way that will keep them from collapsing. Okay, so this shouldn't take long. I'll give you a minute. And then Elizabeth, you're going to do it for us. Okay, Elizabeth, what did you get for the first one, the triangle? What did you draw in there? Nothing? Correct. It's a triangle. It's super strong. So the solution is to make triangles. So on the next one, I drew in just a brace. Did you do anything different? Just made two triangles out of it. What did you do for the pentagon there? You drew two lines? How so? Yeah. So actually, because it's symmetrical, we just rotate it, right? That's what I did. Is that what you did? That's exactly how you did it? Nice job. All right, now how about the next one? Now there's a couple different solutions for this one. So why don't you come up and show us how you did it? Okay, so you connected those. So here's how I did it. And you show me if yours is yours similar, maybe just on a different side, or did you do it slightly different? That dot to that dot? Okay. Good. I mean, yeah. So again, there's no correct. Well, there's an incorrect answer. The incorrect answer could be your building falls down, right? But there's many solutions to that one. So pretty simple stuff, right? All right. So now we get to, this is the first of the semester, the engineering application. A truss is a special kind of engineering structure that's composed of straight members connected at their ends. These members are connected at what we call pin joint. So does anybody know what a pin joint is? What's a pin joint? Yeah, so fundamentally what we mean by a pin joint is that it can move, right? So in this case, right, it will stay in the same location, but it can pivot. Whereas like a slide joint would be able to actually like move back and forth. That makes sense? So the two things that come together at a pin joint can technically move. Now, obviously, if we were building a real bridge, we're going to do what to it? Weld it, rivet it, something like that to try to get it from moving. But the idea of the pin joint, and the reason we look at this in the ideal structure is if you design your bridge correctly or if you design your structure correctly, it shouldn't matter that those points can rotate because nothing will be able to rotate because the whole thing will be solid, right? So the idea there being that one of the weakest point in your bridge isn't going to be your metal. It's going to be the screw holding it together, or it's going to be the weld, right? So the idea there being that if we imagine everything as this ideal thing that can pivot, and we make sure that that thing won't pivot, you won't be putting the stress on the joint. You'll be carrying the load in the material itself. Does that make sense? Or I should say in the structure itself. Okay, so the truss design takes advantage of the geometric stability of the triangle, right? You can very easily look at that and see a bajillion triangles in there, right? Right? There's not just the little ones, but you're making bigger triangles within smaller triangles. When correctly designed, trusses are very strong for their weight, which makes them a very efficient way of spanning long distances. That's why you see them all over the place, okay? So, a bridge structure constructed with an unbraced quadrilateral to center, like this guy, because remember these pin joints swivel, so if I were to put a load right here, look what would happen to my bridge. All of my bars are still the same length. They're not breaking. So now all we're doing is we are essentially using the strength of the joint, and we're not utilizing the strength of the material. What we want to be using is the strength of the material. And why is that? Right, it's what we just said, right? And that's what I was trying to bring it back, and you got it, right? The joints, again, are our weakest spot. So we want the strong material, right? We're going to be making this out of iron. We're going to be making this out of steel. That's very, very strong material, right? We want the material to be carrying the load and not the joints, okay? So what would I do? What would you guys propose that I do to this bridge or to this truss to make it not do this? Add a brace or a tie, okay? And how would we do that? What do you think, Malika? Okay, make another triangle out of the square. I think I agree 100%. Okay, so very simply, this structure right here, super weak. All we need to do is add one more engineering member to, or one more structural member to it, and just brace it. And now it can't go anywhere because we have nothing but triangles. The only way for this thing to deform is for something to actually break. Right? So we'd actually have to break the bridge over our river to get this to deform. Whereas for the one on the above, if we had that over a river, it would just have to blow really hard. Okay? It's going to be a bad day. All right. So that is the end of the lecture. Right? Pretty simple stuff. Okay? I don't think I rocked anybody's world tonight. It's all pretty basic stuff. We did geometry, we did trigonometry, which you guys all have under your belts, and now you guys are ready to be structural engineers. It's pretty sweet. Okay, so we have a super cool lab tonight. I bought these kits last year, and they're pretty awesome. It's nothing, I couldn't come up with anything better than this. I do have a shout out to Connects in the book because they helped us out a little bit with this. But these are bridge kits, so what we're going to do is when you guys get back, we're going to split up into groups, and then I want to work through I want you guys to work through the activity that we have for tonight, which is, I forget which one, but we'll find it. It's the bridge activity. Can somebody find the number for me, actually? There you go, right there. It's Lab Unit 8 for tonight. Okay, Introduction to Structures, Truss, Bridges, and that is on page 143. So page 143 is what we're going to be doing tonight when you guys get back. So please take a 5-minute break. And then what we're going to do when you guys are all done is we're actually going to combine our sets together and make a super bridge, and you're going to see how this stuff actually works, okay? All right, so 5 minutes, and I will see you guys back. Thank you very much.